which is on resilience and home space for WSTS. And the talk is given by Mathieu.
So I'm going to talk about resilience for well-structured transition systems. First, I want to give a little bit of motivation behind resilience and its concept. And then I'm going to talk about WSTS and what's decidable about them. So imagine you're in a situation like you're at home and you have your fridge and you are going to say, all right, good situations is when the fridge is going to have a low enough temperature. And a bad situation is going to be when the temperature is too high. So normally, when we look at verification and safety properties, we ask the bad states to never be reachable. But here, if you reach a bad state, it's not going to be dramatic. If you have like 2 degrees more than the optimal situation for 5 seconds, and then you go back to a low enough temperature, then you're fine. Which leads us to asking the question, rather than bad state never being reachable, is it possible always when you reach a bad state to go back to a good state? Which is what we call the resilience. So the general resilience is going to be if you're given a set of safe configuration and a set of bad configuration, which is going to be, for our purpose, the complement of safe, then is it always possible from bad to reach an element of safe? And when I talked about the example of a fridge earlier, you see that it's important to be able to know the number of steps necessary to go back to a safe state. Like if you stay too long in a bad state, then it can be dramatic. So we have a variant which is K-resilience, which asks, is it possible to go back in atmos K-step? And bounded resilience, which asks, does there exist a case such that K-resilience holds? So if you look at an example, so for instance, in a vector addition system with states and reset, so here you have control states, you have counters, here only one counter, which can be incremented, decremented, and reset to 0. And you say, okay, what does a safe state look like? So for instance, you can say, okay, you have control state Q0 and any natural. And then resilience is not going to be satisfied because if you are in Q1, you can never go back to Q0 again, basically, in this example. And okay, but so what's another example? So you can say, okay, what if the only safe configuration is Q1 0? And then resilience hold because you're always going to be able to go back to Q1. And then in Q1, you're always going to be able to go to Q1 0. But bounded resilience does not hold because if you have a sufficiently high number of the counter in Q1, then you're never going to be able to reach Q1 0 in a small number of steps. But if, for instance, you add a transition from Q1 back to Q0, which does +1 to the counter, then bounded resilience holds because 6 resilience hold. So because, for instance, if you're in Q1 with counter value 6, then it's going to take you 6 steps to go back to Q1 0. But if the counter value is too high, for instance, if you're Q1 9, then you can use this new transition to go to Q0, and then you can go to Q2, and then you can reset the counter to 0, and you reach this safe configuration Q1 0. And so here we've talked about, like, is it possible for every configuration which is in bad to go to a safe configuration? But some configuration in bad are not necessarily reachable. So you can ask yourself, is it necessary to check resilience for those as well? Or rather, should we only consider those bad situations that are reachable? Which lead to a variant which we call state resilience, where basically instead of asking for a path from any bad configuration, you ask for reachable bad configuration from an initial state. So this is a problem we are concerned with. And the model we have been looking at is that of well-behaved and well-structured transition systems. So a well-behaved transition system is an ordered transition system where all your anti-chains are necessarily finite. So every set of 2x2 incomparable element is finite. And moreover, your transition relation is compatible with the order. So for all S1 and S2 bigger than S1, if you can go from S1 to T1 in one step, then there exists T2, which is larger than T1, and which is going to be reachable from S2. And a well-structured transition system is just a WBTS, in which the order is also WQO. And now, in general, for WBTS and WSTS, the resilience problems are undecidable. So our goal has been to look at which subsets of WBTS and WSTS are such that the problem is decidable. So here is like a kind of taxonomy of WBTS with WBTS, WSTS, and also omega squared WSTS, which is just a variant with a subset of WQ. And we can see that a lot of classical systems, such as Petri nets or contour machines, are comprised inside those larger models. And so we're trying to say, what is the largest model such that resilience is decidable? And so here are our results of decidability in green for resilience, in blue for bounded resilience and K-resilience, and undecidability in red. I don't know if you can see from far, but basically what we've been trying to do is to draw the line between what's decidable and what's not decidable. So I want to zoom in a little bit in the case where safe is upward closed. We've been looking at upward closed or downward closed safe sets because we want to look at infinite sets of configuration which have finite representation. So, for instance, here, before going into the results, I want to introduce some classic notions. So, an ideal is a set that is both downward closed and directed. And ideals are useful if all your antishines are finite, because then all the downward closed sets can be expressed as a decomposition into a finite number of ideals. And then what we also ask for the system is effectivity, which is basically we ask that classic things are decidable, like the transition relation or the ordering and membership. So now our results basically states that if you have a well-behaved transition system where you are effective and you're able to compute the downward closure of post applied to any ideal, which we call post-ideal effective. And if your compatibility, moreover, is strong, meaning here T2 is reachable from S1 in exactly one step, then resilience, bounded resilience, and K-resilience are going to be decidable. And I want to give an idea of why that is. So if safe is upward closed, then you can express safe as the upward closure of its basis, and then resilience become an infinite number of coverability questions, meaning for every element in bad, you ask whether it's possible to cover an element in the basis of safe. And what we're looking at is we're looking at the completion, which I'm going to introduce in a moment, and we're saying that if you can cover an element in a WSTS, then you also have a cover eligibility property in the completion. And this enables us to go from an infinite set of coverability questions to a finite set of coverability questions. And since coverability is decidable, then we are able to decide the problem. So I'm going to talk about the completion now to introduce what this is. So the completion of a WBTS is you're looking at an order transition system where the set is instead the set of ideals rather than S, and your order is the inclusion. And now your new transition relation is you can go from I to J if J belongs to the finite ideal decomposition of the downward closure of post of I. And now if you have a path in the WBTS from X to Y, then naturally by construction you're going to have also a path of the same length from an ideal A to J if they contain the downward closures of X and Y. But the converse is also true, meaning if you have a path in the completion from an ideal A to an ideal J, then you're going to be able to construct a path in the WBTS also. And moreover, if you have this strong compatibility hypothesis of from the theorem, then the length of the path are going to be the same, meaning that you're able, if you have to look at the coverability questions in the completion, and then you can check for the length of the path. and decide K resilience and bounded resilience for the WBTS now, and L resilience as well. So this was just for like this large section of like if safe is upward closed and you're looking at resilience. In the case of state resilience now, so when you look only at the reachable bad configurations, there exists a result of decidability by Oscan and Voderman. And what we've been doing with Alain is basically we've considered extension of the results because they consider basically only the bounded and state resilience cases. And so what we've done is we say if you look at resilience, then you can lower some of the hypotheses. And we've also provided some undecidability results. So this was when the case where safe is upward closed, and you can reduce things to coverability questions. But now I want to talk about when we consider a downward closed set of safe configurations. So if you have a downward compatibility for your WBTS rather than upward compatibility, then you're going to be able to have symmetrical decidability results. But this is not what I'm interested in right now. What I'm interested in is vector addition system with states, which are not downward compatible, and where we manage to also provide some kind of decidability results. So if I go back to a quick definition of vector addition system with states, so you have a set of control states, you have a set of counters. Here, for instance, you have two, and you can increment or decrement the counters. And now I'm looking at a safe set of configurations, which is downward closed. So for instance, here, I'm asking that I am in Q1 and that the counters do not exceed value 3. And then here, resilience hold, because as before, you can always go to Q1 and then you can always lower the value of the counters. But bounded resilience in this precise example does not hold, because again, if you are too large, then you cannot go back to safe in a finite number of steps, in a small number of steps. And what we've seen is that resilience itself is decidable for vector addition system with states and vector addition system with states over the integers when safe and bad are both semilinear sets. And this is due to a result by Yankar and Leroux about another problem, which is the home space problem, which asks basically that post-star of a set Y is included in pre-star of a set X. And so here we see that if you replace X and Y by the set bad and safe of bad and safe configurations, then it reduces itself to this home space problem. And for vector addition system with states, we've shown that bounded resilience and K resilience are both decidable when safe is downward closed. And a funny thing is that if you look at vector addition system, so which are basically vector addition systems with states with only one state, then bounded resilience and K resilience never are going to hold. So to conclude, what we've done is we've tried to really draw a line between which model have decidable properties and which do not. But we have only been concerned so far with decidability itself and not, for instance, a complexity analysis. So for instance, here for reset vector addition system with states, we've shown that it's decidable, but we don't have any idea about what's the precise complexity of deciding the problem, which could be a next step in future works. Some other kind of stuff, as I mentioned briefly, when I talked about vector addition system with states, we have decidability results when bad and safe are semilinear sets rather than just upward or downward closed. And this can be also a further avenue of consideration, like considering what kind of safe or bad states can provide decidability. Another last thing to consider could be now, once you can decide resilience, you can also ask synthesis questions like, is it possible to build the maximal set of safe states such that it's going to be resilient, which is a different question altogether. So here are some references to the articles that I talked about, like from Yankar and Leroux, or from Ogazan and Wudeman, and you can check them out. And thanks for your attention. I will not be taking any questions. Oh, okay.
Thank you very much, Alex.
So if I have understood correctly, resilience means that you can go from a bad state back to a safe state.
Yes, exactly.
And shouldn't there be a notion that you will always go back to a safe state from a bad state? I mean, this is a little bit like stability, right? And
Yes.
Maybe in, since you mentioned synthesis, whether there exists a strategy such that you will always go to a safe state from a bad state.
Yes, so this is another question that can be asked. It's not necessarily going to be relying on the same methods because, for instance, coverability is decidable for well-structured transition systems, but now you're asking whether you're always going to cover, which is a different question altogether, which is harder to solve. So, but this can also lead to a variance of the problem. Also, one of the things is that we've looked at a lot of variants on how do you cover, how do you reach. So, but this could be also up for future works, looking at systems such that you're able to decide whether you're necessarily going to go back to a safe state.
Any more questions?
If I have understood correctly, like for the Alain. If I understand correctly, for VASS, the resilience, when you have the safe states that are semilinear, you have a complexity that is Ackermann, no?
Yeah, that's from the result of Leroux and Yankar.
Yeah, okay.
Yeah.
Okay, any more? No more questions? Then thanks again to the speaker.